Now, I already mentioned that entanglement is a key feature of quantum systems that sets them apart from classical systems. And this can indeed be quantified in terms of so-called Bell inequalities. These are due to the same physicist John Bell, whose name is associated with the Bell pairs that we encountered as examples of maximally entangled states in the last segment. Now, there are various versions of these Bell inequalities, but the simplest one, the one that we are going to discuss here, is known as the CHSH inequality. And again, these letters stand for the names of different physicists: Clauser, Horn, Shimoni, and Holt. And this inequality is particularly interesting because it corresponds to a particular physical experiment that has been carried out for different quantum systems and indeed has been taken as the indication that our world is fundamentally a quantum world and not a classical world. Now, these experiments are carried out on composed systems made out of two parts which are both two-level systems. But to put this into a very concrete physical context, I'm going to assume that these are the spins of two electrons. So we will have a spin up or a spin down for the first electron, and a spin up and a spin down also for the second electron. So we have our first spin here and our second spin here, and these symbols simply indicate the two possible states that each of these spins can be in. So these are the states of the two different two-level systems, the two parts of the quantum system for which we would like to study their entanglement. Now, on each of these spins we can carry out experiments, and for these inequalities we are just selecting suitable observables for these experiments. And these are the following: A1 and A1 prime for the first spin, and B2 and B2 prime for the second spin. And we are going to assume that the outcomes of these experiments are always either +1 or -1. So these are just like our Pauli matrices. So there are only two possible outcomes, +1 or -1 for each of these experiments. Now consider that we collect all the data from these experiments in the following way: by defining a certain composed observable f, which just takes these outcomes. And for the outcomes themselves, I'm going to drop the hats. These are just now numbers. These are the possible outcomes of these experiments. And this is given by this following expression. This is just a convenient expression for the sake of these inequalities to collect all the data from all of these experiments into individual numbers. So we are going to carry out these experiments and then combine the results in the way given here. And now these combined values are restricted in a very simple way. Namely, either we will find the same outcomes for these two observations here, and then this term will be finite, and it will be either +2 or -2, and it will then be multiplied either by plus or -1 from the observation on the second spin. So we will get a result which is plus or -2 from this term here. And from the second term we will not get any additional contribution because these two terms A1 and A1 prime then just cancel because these outcomes were assumed to be the same. And if we observe opposite values in these experiments on the observable A1 and A1 prime, then this term here will cancel. And here again we will obtain plus or -2, either these two add up with the same sign or with opposite sign. And again this will be just multiplied by plus or -1. So at the end of the day we just get plus or -2 again. So the possible values of this combined quantity f are just plus or -2. So this is a very particular restriction for this combined measurement observable f. And indeed, if we average this over many different observations and then take the absolute value of this outcome, this will certainly be never larger than 2, because we are averaging numbers between plus and minus 2. And on average, this will never give us a result which is larger than what we have in this range. But what we assumed by putting in individual numbers into these different places is that we can actually know all of these different numbers at the same time. And this is not true in the quantum setting. In the quantum setting, we have to elevate this to an observable made out of the operators for the individual observations. And of course, we have defined how these operators look like. They will just be 4x4 matrices made out of blocks of 2x2 matrices in the way that we have defined it before. Now that we have elevated this to an observable, we can apply this to all general observations, including observations involving non-simultaneous observables. In particular, we can apply this to the situation where the observations on the first quantum system involve the Pauli matrices Z and X, and the observations on the second part of the quantum system, the second spin, involve the following combination of these matrices. Now these expressions contain some convenient factors so that our final expression will just be simple. And one can also check that these operators for the second spin indeed just have eigenvalues plus and minus 1, so that we have the same constraint on the observable values as we required at the outset. Now each of these observables correspond to a 4x4 matrix, and therefore we can work out the corresponding 4x4 matrix for this composed observable F simply by matrix multiplication and by then taking sums and differences of matrices. So the result will be a 4x4 matrix, and I simply give you this result here. This can be easily checked by carrying out these matrix multiplications and operations. Now this is an observable of our composed quantum system, and we can work out the expectation value of this by following the general rule for expectation values. So an expectation value of this observable would be obtained by multiplying this by a quantum state from the left and to the right. And now we can select any kind of quantum state that we want. And we will get an interesting result when we there select a maximally entangled state. So for instance, we can select the following state, just as an example. Which happens to correspond to one of these maximally entangled states, namely the Bell pair beta 1, 1. Now in terms of spins, this is the state in which the two spins are always opposite. And these two different possibilities are in a superposition with the minus sign. So this is the origin of this minus sign here. And now if we work out this expectation value in this particular state, we obtain 2 times square root of 2, simply by the multiplication of this vector from the left and the right with this matrix. And now this turns out to be a number which is larger than 2. So this seems to violate the condition which we have derived above. How is this possible? Well, in the derivation of this inequality, we essentially applied classical logic. We allowed that these outcomes are probabilistic and possibly even correlated, but what we could not account with the reasoning given up here is that these outcomes might be correlated in a very particular way that is only possible in a quantum system. And this correlation is a manifestation of entanglement. So in these maximally entangled states, we obtain some correlations which cannot be reproduced in classical systems based on the reasoning given here. So this is the reason why we consider entanglement as a genuine quantum effect that sets quantum systems apart from classical ones. Now, the corresponding experiment has indeed been carried out for the first time in the early 1980s on photons, which have polarizations, two different states of polarization, which quantum mechanically behave exactly like the spins that I have described here. And indeed, one could detect in these experiments that these expectation values can violate these inequalities here. So the general name of these inequalities are Bell inequalities, and they delineate the boundary between quantum and classical behavior. And the violation of these inequalities, which define classical behavior, has been indeed observed in experiments. Now, this concludes this first introductory and very general chapter on quantum mechanics, which lays the foundations of everything that is going to come in terms of information processing. So we want to use quantum systems to process information, for instance, for communication or for computation. And in there, these two-level systems will play a natural important role because they are the fundamental unit in which we can encode information of a system. And then we can process this information by evolving the quantum system over time. So in terms of general foundations, we have covered everything. From now on, we can focus on what all of this means in terms of information, and we will first do this on the classical level.